Hi. What Jonathan doesn't say is that I'm his PhD. Thank you for inviting me. My talk will be about testing how an actual existing method to make interpolation or fitting a manifold is good on a sphere S2. So just to fix the ideas, when we talk to manifold, we talk about manifolds. It's about a space, curved space, where the points are the same. Here it's an example. It's the SO3 manifold, so the orientations, or it can be a manifold of shapes, whatever. It's just something with data points, and they all look together. They all look like the same. They have the same structure, and we would like to fit a curve there in blue, and would like this curve to be C1. And one of the applications that motivates this fitting on manifold is, for instance, the wind field estimation problem. So this is just an example. I will not talk about that afterwards. It's just to say, hey, actually it's cool. So, what is the wind field estimation? It's, well, imagine you want to control a drone, or you want your drone to control himself, and the drone is inside a city, and in that city there is a prevalent wind they say that the weather, this wind has a certain magnitude and a certain angle. And you can know actually the profile of the wind everywhere in the domain, everywhere in the city, even if there are buildings that make turbulences between them, just after them. And actually, computing this is fluid mechanics, and the guy who are doing fluid mechanics, they say, hey, it's very hard to compute that, it takes a lot of time. We should have an idea to find this solution, but faster. And they observed that the wind configuration in that domain can be represented as a matrix, a semi-definite positive matrix of rank R. It's a covariance matrix, so if you have a domain of n by n, you have a matrix of n squared by n squared. And an idea here, as this space has a structure of manifolds, would be to fit a curve between points here, C1, C2, C3, compute it offline for certain orientation of the wind or certain magnitudes of the wind. And when the weather says the prevalent wind will be something different than the one for which you have data points, you could just take the solution on the curve and say it's a good approximation. So this is the motivation. So during this talk, it will be divided in two parts. First one, it's the explanation of how the fast method works and why it is suboptimal. And I also will do some reminders of Bézier, because I will use Bézier functions. And in the second part, I will talk about an accurate method, which is way less efficient. And of course, I would like to compare them. So first part, the fast method is based on Bézier function, because actually it's quite convenient to work with that, because a Bézier function is just driven by the control point. And the idea is, between each consecutive data point, we construct a Bézier function. So all we have to know is, between these, where do we place the green points, so the control points of the Bézier curve, and how do we glue them together such that the curve is C1. So the only points we want to find is BI and PI. Why do we use Bézier curve? Because it's easy to generalize to manifolds. And it exists an algorithm called the Decasseur algorithm, which is only based on geodesics. The idea is the following. So you parameterize your Bézier curve between 0 and 1, and you would like to know what is the evaluation of this Bézier curve at, for instance, a quarter, half, and three-quarter. The basic idea is you draw geodesics, or you draw straight lines. On these straight lines, you just compute the value of these lines at a quarter, like this. And between these points, you again draw a geodesic, and you evaluate it at a quarter. And if you do that for the other values of the point, of the parameterization, you do this, then you draw a straight line, you evaluate them, at the end, for a large number of points, you can draw the basic curve. So if you replace this by geodesics, it's easy. You can directly upgrade that to manifolds, and this is a result on the sphere. So yeah, well, you have to believe me. It's an act of faith. Here are the data points, and this makes interpolation. You choose the control points even randomly, and you have a fitting curve. But here it's kind of ugly, and the control points were chosen randomly, so we would like to know where we have to place them. So to do so, we decided to minimize the mean square acceleration of the curve such that you don't have the curve doesn't turn too fast on the main. So here you have the Bezier spline, and you take the second derivative. Here we are on the Euclidean space. You will see why after. And this is the constraint to have a C1 curve. So on basic curves, this constraint ensures that you have a C1 curve when you glue two basic curves together. And actually, as we use only quadratic and cubic basic curves for the Bezier spline, this equation here is just a quadratic equation. So if you derive it, you have just a linear system, and you can find very easily the solution. So the xi here are the points p0, pi, and pn. And this solution is just an affine combination on the data point. So it's very easy to lift this from the Euclidean space to the manifold setting. And this is where suboptimality arises. So this solution here is optimal on the Euclidean space, but the solution we will have on manifolds is not specially optimal on the manifold. So what we observe that this solution should be invariant to translation, and we interpret this difference here as a logarithm. So we represent the data points on the tangent space of this DRF. We do the affine combination according to the weights here computed on the Euclidean space, and from the point we obtain, we map it back to the manifolds, and we obtain the point xi like this. So actually we have no guarantee that this is optimal. Just here, small solution. This is a curve obtained by this fast method, and here I have a video. So if these orientations are the data points, an interpolation is given by this. So you see that the curve is smooth, at least, and it doesn't seem to accelerate too fast. So visually, it seems that the solution is close to optimum, but we would like to have a better idea of this. So we dig a little bit, and now I switch to the other part of the talk. So, as I said, the solution x star here is an estimation of this objective function, and we tried numerics. So we transformed the mean square acceleration into second order finite differences to create this objective function, so we can use it with MATLAB for instance, and we will compute this x tilde, which is a solution of this. So x tilde contains all the control points of the Bezier spline. And the hope is that this x star is not too far from the x tilde. So, because, well, actually, in the first step, what we thought is, okay, deriving this on the manifold is quite complicated, so, okay, we take the bazooka and we just use derivative-free optimization using MANOPT, but it takes a while to compute the solution, so we decided to work on a sphere with not too much data points and not too far from a geodesic. So the data points are actually corrupted version of points, equally spaced points on the geodesic on the sphere. So the solution should be easy to compute. and even that wasn't that easy. So we computed x tilde and x star, and we compared them, and what we observed is that actually the fast solution is of course different from the more accurate solution, but it diverges only of 2%, the order of 2%, which is quite acceptable. It depends of course on the application, but we were quite surprised. Actually we couldn't go further than 10 points because the computation is longer and longer because of the derivative-free methods. So actually the next step would be, okay, can we compute a gradient in that? And as I said, computing the gradient of this is not so easy because, well, first you have to know what is the gradient of the second order derivative on manifolds, and you have to compute the derivative of a Bezier curve, which is, if you remember this drawing, it's a geodesic of another geodesic of another geodesic, and so on. And plus you have the C1 constraints, so not that easy. But this is a joint work. We are starting with Ronnie Bachman. He will talk just after me about something else. And we are quite close to a solution. We hope that using this with the gradient, we will be able to do gradient descent and have better bounds on the error we do with the fast algorithm. So here, actually, finding the gradient of a second order derivative, it already exists, and we think that using Jacobi fields can bring us a good approximation of the derivative of the gradient of the geodesic. Well, this is the end of my talk. If you have any questions, I'm open. Please.
So we are well on time. Questions?
There's a theory about splines and polynomials on manifolds, so I'm wondering how it compares to the curves you defined here.
Sorry, I didn't understand the starting of the question.
There's a theory of splines and polynomials on manifolds, so second order polynomials, for example, or third order polynomials. So I'm wondering, so I guess they will also fit in here as curves, right?
So your question is about what if we apply a series of polynomials directly on manifolds?
I think maybe, so my question could be, are the C1 piecewise Bezier curves that you define, are they piecewise polynomials?
Well, on the Euclidean space, yes, because they are defined. On the Euclidean space, yes, it's a polynomial because it's defined on Bernstein polynomials, but on manifolds, actually, I don't think so, because, well, on the Euclidean space, you can construct the Bezier curve differently with the Cassellio algorithm or using a mean. So you can see that you use the Bernstein polynomials and you do a mean. On the manifolds, depending on the method you use to compute the Bezier curve, it brings different solutions. For instance, well, what you could do is, well, for Bezier surfaces, for instance, so you have a point here, a point here, a point here, a point here, and you would like to compute the plane between these points. Well, it's also a Bezier curve, but in 2D, and it's also a sum of these control points here, B0, 0, and so on, times some coefficients, which are also the Bernstein polynomials. So you could, to compute this, you can use the Cassellio algorithm, or you can just say, okay, it's a weighted sum of these control points. But on manifolds, if you try to apply the Cassellio algorithm just by representing that point these points in the tangent space of that point, you see that actually you cannot construct a geodesic plane. You have here and here lines which are not geodesics. So even there, the solution between, the difference between the Descartes algorithm here and the weighted sum here is trivial because one gives a geodesic plane and the other one just gives nothing. Does it answer your question? I don't have I don't think I have the good answer, but this is all I can say about it.
But perhaps it's something to explore if
Yep.
they are polynomials.
Any other question?
So when you say suboptimal, so it's for the, so you use the objective function that you had for Euclidean space. So you take the same objective function for the manifold. So would it make sense maybe to change the objective function? Or, I don't know.
Actually, it's not exactly that. It's just we compute the contour points based on the solution we obtain in the Euclidean space, and we see that the solution in the Euclidean space can be generalized to manifolds. So, so again, I like the board, but we have the objective function here on the Euclidean space. We obtain the optimal solution there, and here we move this to the optimal solution on the manifold. And if we do the same here, we transfer this objective function, which is the mean square acceleration is minimized, to the manifold here. We are not sure that this link is still good. And this is what we wanted to see.
I had a question on the, so you had a formula that you wanted to compute the derivative, yeah, so the d square xyz, I'm not completely sure what it is.
D square.
So the function that you want to differentiate?
This?
Yes.
It's
It's the approximated Laplacian, something like that?
So it's the second order phase difference, which represents this objective function here. So you have a...
So it's based on the Riemannian distance, basically?
Yes.
Okay, so the derivative of that is normally, well, the first order derivative is the log, the second order derivative is directly the connection. So what you have appearing there is the curvature. So the correction that you should find for the accuracy should be linked to the curvature tensor. And actually, I'm pretty sure. So for the sphere, we know the computation of the Hessian of the distance. So I don't know if it's applying directly to this formula, but it should be close. And basically, what I would I mean, if you make something with your time step, well, the length of each of the steps that you're doing, and you relate that to the curvature of the sphere, that should be the criterion that is characterizing somehow the accuracy that you can have. So that's a guess, but I just wanted to point out that, I mean, what is the derivative? I mean, if you're going to the second order derivative of the square distance, that's directly the connection which is there. In constant curvature spaces, it's workable. Not very nice, but workable.
Thank you.
Okay, I propose that we move on to the next speaker, so thanks again.